Hello, we are back talking about eigenvectors and eigenvalues. And let's just remind ourselves what an eigenvector and eigenvalue are. Okay, so we have an n by n matrix A, and a vector is an eigenvector if when we multiply it by A, we get back just a scalar multiple of it. So this is the eigenvector, and this is lambda, that scalar, is the eigenvalue. All right, so we saw in the last video you can check if a specific vector is an eigenvector by just multiplying them together. Just literally do A times U, and C is that some scalar times U. All right, but how do we check if lambda is an eigenvalue for A? Okay, so lambda is an eigenvalue. So we need to check, basically it's an eigenvalue if it has eigenvectors. So are there any vectors x such that this happens? Such that when you multiply that x, you get that specific lambda times x. Okay, and as stated, that's not really an equation that we can answer easily. But notice there's an x here and an x here, so we could change up that equation a little bit, okay, and subtract the lambda x to the other side. And what's left on the right side when we subtract that whole vector off? Well, just the 0 vector. So this is looking a little better because we have 0 on one side, so that's what we need when we're talking about a homogeneous linear system. But this is still not like that because there's 2 vector terms here. So what we notice, right, we have an x here and an x here, and let's factor that out. Okay. All right. And that's really nice. That basically looks like a homogeneous system. Okay, but the question is what's left here? So when we factor this x out, we've got A, and then minus lambda, but we can't just have a real number here because a matrix minus a real number doesn't really make sense. So what we do is we can kind of write this like this instead, right? If we do lambda times the identity matrix and then multiply that times x, we'll get the same thing because identity matrix times x is just x. So really, this is A minus lambda I. Okay. And that is nice because this is just a homogeneous equation that we can solve with row reduction. So to check if a specific real number lambda is an eigenvalue, right, we want to know, are there any vectors x, and these vectors need to not be 0. So we want to know, see if there are non-trivial solutions to A minus lambda I x is equal to 0. And you can do that by row reducing. All right, let's go ahead and see an example of that. Is lambda equal 4 an eigenvalue for this 3 by 3 matrix A? If so, find a corresponding eigenvector and a basis for the eigenspace. Okay, so let's talk about this terminology first. Well, actually, just kidding. Let's talk about how we're going to answer this question. So is lambda equal 4 an eigenvalue for A? Okay, so what we need to do is solve A minus lambda I times x is equal to 0. In our case, that is A minus 4 is our specific lambda I x equal to 0. So we need to figure out what that matrix looks like. Okay, and let's write down our matrix A, 3, 0, negative 1, 2, 3, 1, negative 3, 4, 5. Okay, and is that correct what we have? Yes, that's correct. Okay, so we want to do minus lambda times the identity for And it's the appropriately sized identity, so 3 by 3. Okay, and notice, right, when we multiply that scalar in, all the zeros are going to stay 0, and then instead of 1s along the diagonal, we will have 4s along the diagonal. 3, 0, 1, 2, 3, 1, -3, 4, 5, minus 4, 0, 0, 0, 4, 0, 0, 0, 4. Okay, and now we want to figure that out. So you just do entry by entry. 3 minus 4 is -1. 0 minus 0 is 0. So basically the upper right corner and the bottom left corner don't change because they're all minus zeros. Okay, so 2, -3, 4, and that 1 don't change, but here 3 minus 4 is -1. 5 minus 4 is +1. Okay, so this is a minus 4i. And remember, we were concerned about a minus 4i x equals 0. So how do we solve that? We just take this matrix, augment by 0, and row reduce. And remember, what we're looking for is, does this system have non-trivial solutions? Okay, so let's talk about how we're going to determine our answer for just a second. All right, so non-trivial solutions, how do we tell when we're row reducing if a system has non-trivial solutions? You look for free variables. So if you end up with a non-pivot column with a free variable, that means that your lambda is an eigenvalue, okay? And if there's only the trivial solution, if there's no free variables, then lambda is not an eigenvalue. And so let's think about, just take a little aside here. So we have a 3 by 3 matrix, a square matrix. We're talking about whether there's free variables or not. So you might be able to guess we're going to connect this eigenvalue stuff to, we're going to end up connecting eigenvalue stuff to the invertible matrix theorem. We're not going to do that right now, but we will in the future. Okay, so let's get started with row reducing this to figure out whether or not it's an eigenvalue. So we're just trying to get down to free variables or no free variables. Okay, let's see. I am going to use this -1 to clear out this 2. So I'm going to do 2 times row 1. That's going to be -2. 2 times 0 is 0. 2 times -1 is -2. 2 times 0 is 0. Okay, and I am going to take that and add it here. And that's going to give me my new row 2. So 2 and -2 is 0. -1 and 0 is -1. 1 and -2 is -1. 0 and 0 is 0. Okay, and then I want to I'll use that -1 to clear out this -3 as well. So we want to multiply by 3, but we want it to be positive. So let's do -3 times row 1. -1 times -3 is 3. 0 times anything is 0. -1 times -3 is 3. 0 times anything is 0. And then we're going to take this and add it to row 3 to get our new row 3. So -3 and 3 is 0. 4 and 0 is 4. 3 and 1 is 4. 0 and 0 is 0. Okay, and then we have our first row. I'm going to go ahead and scale so I have a positive 1 in my pivot. So change the sign of everything. 1, 0, 1, 0. Okay. And here we go. All right, so we're actually at a point where we have enough information to be able to tell what our answer is. Okay, so if we think about our pivots, okay, pivot here, and then look at these two rows. What's going to happen when we keep row reducing those two rows? Well, let's go ahead and find out. Okay, I am going to do, let's see, I'm going to use this -1 to clear out the 4. So I'm going to do 4 times row 2, and that's going to give me 0, -4, -4, and 0. And then I'm going to add those together. Okay, so we are going to get our first row didn't change. I'm going to go ahead and scale our second row so it's positive. So change the sign of everything in there. And then what happens when we add these together? 4, well, first of all, 0 and 0. First entry is 0. 4 and -4 is 0 in both of those. Okay, so now we can see pivot in the first column, pivot in the second column, no pivot in the third column. So our answer is yes, A minus 4i has non-trivial solutions, okay? And what that tells us is that, yes, 4 is an eigenvalue. Lambda equals 4 is an eigenvalue. Okay, all right, so that's what you do. You do A minus lambda times I, augment by 0, figure out are there non-trivial solutions or not. Okay, so yes, it's an eigenvalue. And you might remember, let's come back up here. If so, find a corresponding eigenvector and a basis for the eigenspace. Okay, so that's kind of a lot of terminology. And let's write some of that down. Okay, so, all right. A corresponding eigenvector is just any specific solution. Any specific solution to this equation. Okay. Because really that's a specific solution to ax equals 4x. Okay, so corresponding eigenvector is a specific solution, all right? And to get a basis for the eigenspace, let's just talk about the eigenspace, okay? The eigenspace corresponding to lambda equals 4, well, that's just, instead of talking about a specific solution, that's the set of all solutions to ax equals 4x, or another way to put it, remember, is a minus 4i times x equals 0. Okay, that might sound like a lot, but really what we have to do here is just continue our row reduction to write out solutions to this system. Okay, so what we're going to do here is we're going to write our solutions in parametric vector form. All right, and let's go up here. So we had 1, 0, 1, 0, 1, 1. So we solved our system, and we got down to 1, 0, 1, 0, 1, 1, 0, 0, 0, 0. Okay, so we write out our solutions. Any solution vector is going to have 3 entries. Okay, and we know x3 has no pivot column, that one's free, and x1, right, 1 times x1, and then this x3 is on the other side, 0 minus that x3, okay, so negative x3, and x2 is going to be very similar. There's 1 in the x3 column, it gets moved to the other side, so that's minus x3, and then x3 is free, it just stays there. And we bring out that common scalar, and what's left is the coefficient here was -1, -1, and 1. Okay, so a basis for the eigenspace is whatever vectors show up in this parametric vector form. In our case, we just had 1, and that was -1, 1. So we could say that our eigenspace is one-dimensional because dimension is size of the basis. Okay, and then to find an eigenvector corresponding to lambda is equal to 4, well, we just need any vector in this space. So there are lots of answers here, okay? Basically, you could have that vector, -1, 1, -1, -1, 1, or literally any scalar multiple of that vector. Okay. Right, so -1, 1 is fine. You could do -2, -2, 2, right? Anything that looks like that, right? -100, -100, 100. 5, 5, -5, anything that looks like that. All right. So let's talk just a little bit about visualizing this eigenspace. Okay, and this is where the visualizing comes in. So, all right. Here is our perfectly drawn three-dimensional space. There's our x3 axis, our x1 axis, our x2 axis. So I think that works with the right-hand rule. I can never remember. I tell my students I'm always going to use the right-hand rule, and then I can never remember. Okay, so let's look at this. What we are saying is that our vector, right, -1, -1, 1. Okay, let's do that. So -1 in the x1 direction is back. So let's go back here 1. And then -1 in the x2 direction is going to be 1 in this direction. And then up 1 in the x3 direction. Okay, so we want our vector is here, and it's sort of going, right, it's going backwards and up. So it's kind of going backwards and then up. Okay, so our eigenspace is all multiples of this. And what are scalar multiples of a single vector? They are a line. Okay, so what we know is we can visualize exactly what our transformation does. So the transformation Tx equals Ax, where we're talking about the 3×3a from our previous example, okay? For any vector on that line, we know exactly what it does. What it does to any vector on this line, well, it takes it to 4 times that same vector, which is just taking that vector and multiplying the length by 4. So dilates or lengthens that vector by a factor of 4. So visualizing, like graphing a function with inputs in R3 and outputs in R3 is not going to be so nice, but we can at least really clearly see what happens, right? When we take any vector on this line, right? So if I take this vector on this line, feed it through the function, what I will get is that vector multiplied with a length of 4. Not a length of 4, a length 4 times what it was before. All right, that's it.